Right now, thousands of meters below the surface of the ocean, in total darkness and near freezing temperatures, an engineering revolution is taking place. The global offshore energy industry is abandoning traditional shallow water drilling and turning its attention to the abyss. But building entirely new, standalone mega projects on the ocean floor is becoming impossibly expensive. The solution to this massive economic and engineering hurdle is something called subsea tieback engineering. It is a technological marvel that essentially moves the entire production factory directly to the seabed. Welcome to G Fun Facts Online. Today, we are skipping the fluff and diving straight into the engineering, the physics, and the extreme robotics of subsea tiebacks. To understand why this is revolutionizing our world, we first have to look at the problem with aging offshore infrastructure. As a host platform's primary oil or gas reservoir depletes over time, that massive steel facility risks becoming an economic liability. Decommissioning a platform costs hundreds of millions of dollars. But what if, instead of tearing it down, you could connect it to newly discovered, remote reservoirs miles away? That is the architectural concept of a subsea tieback. Instead of spending billions of dollars and waiting years to construct a brand new topside facility to process hydrocarbons from a small or marginal field, engineers simply tie the new satellite wells back to a pre-existing host facility that has spare processing capacity. This host can be a traditional fixed platform, a floating production storage and offloading vessel, or even an onshore processing plant. This incredibly efficient approach drastically slashes upfront capital expenditure and accelerates the time to first oil, all while breathing new life into aging platforms and keeping them profitable for decades beyond their original design life. But connecting a well on the seafloor to a platform 50 miles away is not as simple as laying a garden hose across the sand. The equipment operating at these depths must function flawlessly for 20 to 30 years. We are talking about environments where hydrostatic pressures can exceed 15,000 pounds per square inch. At the heart of this deep water anatomy is the subsea tree. This is not a tree made of wood, but rather a massive multi-ton assembly of high-pressure valves, spools, and fittings installed directly on the wellhead. Subsea trees control the flow of fluids out of the well and allow operators to inject chemicals or gas downhole to stimulate production. When multiple wells are drilled in a single satellite field, their individual outputs are routed to a massive piece of hardware called a subsea manifold. Think of the manifold as a centralized underwater gathering station. It commingles the turbulent mix of oil, gas, and water from various wells into a single larger pipeline, known as the flow line. The flow line is essentially the main artery of the subsea system, carrying the heavy fluids across the seabed toward the host facility. Running exactly parallel to these arteries is the umbilical, which acts as the central nervous system of the entire operation. This continuously manufactured, highly complex bundle of tubes and cables is a marvel of materials science. It is spooled onto massive rotating carousels on specialized installation vessels and laid meticulously across the ocean floor. It delivers electrical power, hydraulic fluid, chemical inhibitors, and fiber optic data communications all the way from the host facility down to the subsea equipment. Through this single umbilical, a human operator sitting in a control room miles away or even safely onshore can monitor well pressures, actuate heavy subsea valves, and inject critical chemicals in real time. And those chemicals are absolutely vital because of a massive engineering hurdle known as flow assurance. Transporting a chaotic mixture of oil, natural gas, and produced water across miles of freezing seabed is a battle against physics and chemistry. In the high-pressure, low-temperature environment of the deep ocean, hydrocarbon fluids turn highly volatile. The greatest threat to the entire multi-billion-dollar system comes from gas hydrates. When natural gas and water mix under these extreme pressures and low temperatures, they form ice-like crystalline structures called clathrates. These hydrates can rapidly accumulate and completely block a pipeline. A hydrate plug is a catastrophic event. It can take weeks or even months to safely dissolve, leading to millions of dollars in lost production. On top of that, waxy crude oils can precipitate paraffin waxes, and heavy compounds called asphaltenes can settle out of the fluid, coating the inside of the pipeline and severely restricting flow like clogged human arteries. To win the flow assurance battle, engineers deploy continuous chemical injection. They use the subsea umbilical to inject thermodynamic inhibitors, such as monoethylene glycol or methanol. These chemicals act like a heavy-duty antifreeze, drastically lowering the temperature at which hydrates can form. But chemicals alone are not enough. Thermal management is equally critical to keep the fluids warm as they travel vast distances. Subsea flow lines are wrapped in advanced insulation materials like aerogels or polyurethanes. However, for extremely long tiebacks, passive insulation simply cannot retain enough heat. To solve this, the industry developed pipe-in-pipe technology, where the hydrocarbon-carrying pipe is encased within a larger outer pipe. This creates an insulating vacuum or a cavity for high-efficiency insulation materials, much like a giant thermos. Taking it a step further, modern mega-tiebacks utilize electrically trace-heated pipe-in-pipe, or direct electrical heating systems. These systems run powerful electrical currents through the pipeline, actively heating it to ensure fluids remain above critical crystallization temperatures, even if the system experiences an unexpected, prolonged shutdown. But even if you keep the pipes warm and clear of ice, you still have to physically push millions of gallons of heavy fluid across the ocean floor. Historically, tieback distances were strictly limited by the natural pressure of the reservoir itself. If the underground reservoir lacked the pressure to push the fluids 30 or 50 miles across the seabed and up a vertical riser to a floating platform, the field was economically dead. This physical limitation sparked the next great leap in offshore engineering, which is subsea processing. Engineers decided to move the heavy processing equipment off the surface platform and put it directly on the seafloor. This suite of technologies includes separation, boosting, compression, and water reinjection. Let us start with boosting. Traditional centrifugal pumps are designed to handle incompressible liquids. If a large pocket of natural gas, known as a gas slug, enters a traditional pump, the pump loses its prime, overspeeds, and can violently tear itself apart through cavitation. Subsea multi-phase boosting pumps are a totally different breed. Installed directly into the tieback architecture, they utilize advanced helicoaxial designs, somewhat similar to the compressor stages of a jet engine. This allows them to impart immense energy to a chaotic, churning mixture of oil, gas, and water, counteracting the friction losses inherent in long pipelines. Projects like the Barracuda multi-phase boosting system have successfully demonstrated the ability to pump high gas volume fluids over incredible distances, turning previously unprofitable marginal fields into massive commercial successes. But for ultra-long tiebacks, pumping everything to the surface is wildly inefficient. Transporting a heavy column of useless produced water alongside valuable hydrocarbons wastes immense amounts of energy. Enter subsea separation technology. Massive subsea separator vessels, built like deep-sea submarines, use gravity to separate the gas, oil, and water right at the seabed. The Passfloor project, off the coast of West Africa, became a landmark achievement in this space. By removing the water early and injecting it back into a secondary well to maintain reservoir pressure, the payload is significantly lightened. This drastically reduces the risk of hydrate formation and spares the topside facility the incredible burden of processing massive volumes of wastewater. In purely gas fields, subsea compression is the ultimate enabler. As gas reservoirs deplete, their natural pressure drops. To solve this, engineers lower a subsea gas compressor to actively suck the gas out of the reservoir, compress it, and force it through the pipeline. The Ormen Lange field in the Norwegian Sea represents the absolute pinnacle of this technology. One Subsea built a staggering subsea multi-phase compression system that pushes gas 120 kilometers to the Nyhamna onshore gas processing plant. This project set a world record for transmitting variable speed power from an onshore facility to equipment under 850 meters of ocean water. The 16-megawatt subsea compression stations are incredibly surge-tolerant and do not even require the well stream to be pre-processed, proving that heavy industrial gas compression can be executed safely in the isolated abyss. Because of these processing breakthroughs, distance records are constantly being shattered. In the early 2000s, Shell Mensa project hit 108 kilometers. BG West Delta Deep Marine pushed it to 112 kilometers. Eventually, the industry had a brilliant realization. If you can tie a field back 120 kilometers to an offshore platform, why not bypass the offshore platform entirely and run the pipeline straight to the beach? The Snøhvit development in the Barents Sea did exactly that, taking production via a record-breaking 143-kilometer tieback directly to a liquefied natural gas plant on the Norwegian coast. Future expansions to the Snøhvit field are expected to push this to nearly 195 kilometers, and proposed concepts like the petrol field off northern Australia envision a phenomenal 285-kilometer subsea tieback directly into Darwin. As the physical hardware pushes new boundaries, the digital infrastructure is experiencing a total renaissance. The sheer complexity and extreme cost of subsea operations demand unprecedented reliability, which has paved the way for advanced digitalization, remote monitoring, and artificial intelligence. Today, digital twin technology is a standard requirement. A digital twin is a highly accurate, real-time virtual replica of the entire subsea network running on powerful computers. By feeding live data from sensors located on the subsea trees and manifolds into advanced multi-phase flow simulators, engineers can visualize exactly what is happening inside the dark pipeline. The AI-driven digital twin can predict the formation of a hydrate plug hours before it occurs, alert operators to microscopic abnormal vibrations in a multi-phase pump, or optimize the flow rate to maximize efficiency. This digital leap is accelerating rapidly. For instance, in late 2025, SLB and Shell collaborated to develop agentic AI solutions using the Lumi AI platform. By parsing vast amounts of subsurface and production data, operators can shift from reactive maintenance to predictive asset management, saving millions in costly downtime. Simultaneously, the physical maintenance of these sprawling subsea networks is being handed over to robotics. Instead of deploying a surface support vessel costing hundreds of thousands of dollars a day every time a subsea valve needs an inspection, operators are deploying resident autonomous underwater vehicles. These advanced robots actually live in subsea garages on the ocean floor, constantly charging their batteries. When an anomaly is detected, the autonomous vehicle deploys entirely on its own, swims through the pitch-black water using high-frequency multi-beam sonar to map its surroundings in 3 dimensions, navigates to the subsea tree, conducts high-definition visual inspections, and returns to its garage to upload the data. Because subsea tiebacks extend the life of fields for decades, the wellbores themselves must be maintained. Over time, they can scale up, produce excessive water, or experience mechanical failures. To fix this, engineers must re-enter the well, spawning a massive secondary industry called subsea well intervention. Historically, this required leasing a massive drilling rig. Today, the industry relies on riserless light well intervention vessels. Imagine trying to thread a needle from hundreds of feet away while standing on a moving floor. These dynamically positioned ships achieve this by constantly firing omnidirectional thrusters to hold the ship perfectly still, even in a raging storm. They utilize a subsea lubricator system connected directly to the subsea tree, allowing engineers to drop wireline tools directly into the wellbore without a traditional riser pipe. In 2024 alone, specialized subsea tiebacks and intervention-ready infrastructure saw investments exceeding $8.5 billion in Norwegian waters, with digitalized vessels reducing campaign turnaround times by up to 35%. Beyond pure technical ambition, this expansion is fundamentally intertwined with the global energy transition. Oil and gas operators are under intense pressure to reduce their Scope 1 and Scope 2 carbon emissions. Building a new 30,000-ton steel offshore platform from scratch requires a colossal amount of energy, steel manufacturing, and logistical emissions. Utilizing an existing host facility inherently lowers the carbon footprint of a new development. Furthermore, the industry is transitioning to all-electric controls. Electric subsea trees and manifolds replace bulky, leak-prone hydraulic actuators with highly efficient electric motors. By powering these mega tiebacks directly from onshore renewable grids or nearby floating wind turbines, the need for offshore gas turbines is eliminated entirely. In the North Sea, the integration of electrified subsea systems is reducing operational emissions by nearly 30% per project. The financial landscape proves that this is the future. Offshore engineering, procurement, and construction contract award values hovered around $54 billion in recent years. Because tiebacks require less upfront capital and generate quicker returns, they provide operators with a lower break-even price per barrel. As we look to the future, subsea tieback engineering will remain the absolute backbone of offshore energy. By merging advanced fluid dynamics, robotic autonomy, artificial intelligence, and heavy subsea machinery, the industry has successfully turned the hostile ocean floor into a sophisticated, interconnected factory. No matter how isolated a hydrocarbon reservoir may be, it can now be safely and economically brought to the surface, proving that the greatest engineering frontiers are not just in space, but hidden thousands of meters beneath the waves. Thank you for listening to this deep dive on Fun Facts Online. Be sure to tune in next time as we continue to explore the incredible engineering shaping our world.